Okay, so this is a nice example problem that tests both our understanding of the forces associated with circular motion and the force of friction. Okay, so let's read the problem. A sports car is rounding a flat curve with a radius r. If the coefficient of static friction between the tires and the road is mu sub s, what is the maximum speed at which the driver can take the curve without sliding? Okay, so this is a really relevant problem for just everyday life. Right? This is going to tell us how fast we can go around a corner in our car without sliding off the road. Okay, in this case, we don't have any numbers. We're going to do this entirely symbolically, and that will give us an expression at the end that we can use and plug in different numbers to and test how fast can we go around a corner. Right, so let's draw a picture of the problem, and I'll do my best to do some artwork here. So we have some kind of a curve in a road, and we have a car driving on this kind of curved path on that road, and we need to figure out how fast this car can go around this corner without sliding. All right, so let's try to draw a free body diagram for this car to represent all the forces acting on the car. I'll draw a dot to represent the car, and I'm going to draw from the perspective of just being right behind the car. So from behind the car, I have the force of gravity acting down, I have the normal force acting straight up, right? And then I have something, there must be some force which is towards the center of the circle, right? Because this car is accelerating towards the center of the circle, right? The velocity vector is continuously changing direction. And at a given moment, the velocity vector is staying the same, the speed is staying the same, but the vector is changing direction, right? So that must mean that the acceleration is towards the center of the circle, which means there must be some net force towards the center of the circle, right? So what force could be acting on the car towards the center of the circle? Well, the only forces involved here are the interaction between the car and the road, so it must be the force of friction on the tires, which is pushing the car towards the center of the circle. All right, so I'm going to draw in a force vector towards the center of the circle. Right? I'll call this F sub s for the force of static friction, right? Because these tires are not sliding. If they were sliding, we would use the force of kinetic friction, but since they're not sliding, all right, we can use the force of static friction. Okay, so we have a free body diagram. I can define my xy axes. I'll make the plus x direction towards the center of the circle. I'll make the plus y direction straight up into the air. All right, this is again from the perspective of being behind the car. And so now we have a free body diagram. Okay, so we have to follow our general procedure that we always follow when we're solving force problems. We draw a free body diagram, we define our coordinates, and then we apply Newton's laws. Right? In this case, we want to apply Newton's second law because we have some net acceleration. Right? We have acceleration towards the center of the circle, therefore there must be a net force towards the center of the circle. Using Newton's second law, we should be able to solve for our unknowns. Okay, so in the x direction, I have that the sum of the forces in x is equal to the mass times the acceleration of the car in the x direction. Okay, as I've drawn it in the free body diagram, we only have one force in the x direction. It's in the plus x direction, so I just add that in here. The sum of my forces is just equal to the force of static friction, and that's equal to mass times the acceleration of the car in the x direction. Okay, at this point, we can realize that this acceleration we have another expression for. Right? We know that this acceleration is a special kind of acceleration. This is our centripetal acceleration or our radial acceleration. Right? This is the acceleration that arises when we're traveling at a constant speed around a circle, and we have an acceleration towards the center of that circle. Right? So we have an equation for centripetal acceleration. It's v squared over r. Right? It depends on our speed squared divided by the radius of the circle. So I can, in this formula, replace my acceleration with that expression, v squared over r. Okay, so that's a good thing because in this problem we want to find the maximum speed at which the driver can take this curve, and we've introduced speed into this problem. Right? We've removed acceleration, and we now have speed in the problem. Okay, now we can again take a quick look at the problem. We want to find the maximum speed that the car can go around this curve. Right? Here's the thing about the force of static friction. The force of static friction will vary, right? This force vector, could be this big, it could be this big, the force of static friction will vary. It'll do whatever it needs to do to keep you stuck to the road, right? It's only at that point where it reaches the maximum static friction, at which beyond that, the car will start to slip, right? For that reason, the equation for the force of static friction has a less than or equal to, right? It's less than or equal to this coefficient of static friction times the normal force. Right? Because again, the static friction force will vary. If we weren't going around a corner, it would be 0. If we're going around a corner kind of slowly, the force of static friction could be kind of small. What we want to know is what is the maximum speed at which we can go around the corner, right? We want to know V max, and so to find that, we need to find the maximum static friction. Right? And it turns out the equation for the maximum static friction is when this becomes an equal sign. Right? That's the maximum that the force of static friction can be before something starts sliding. Okay, so now that we know that, we can replace our F sub s with this equation for our force of static friction. Right? This is mu sub s times n, and that's equal to m v squared max over r. Okay, so we can solve for the velocity here. The only thing is we don't know what the equation for our normal force is, right? And so it may be somewhat obvious to us, but just to make sure we follow the full procedure that we should always follow, to find the normal force, we can always use Newton's laws. I can look in the y direction. I have two forces, and those two forces must add up to 0 because this car is not flying up into the air, falling into the ground. So in the y direction, I can use Newton's first law to realize that the sum of my forces must be 0. I can see I have two forces in y. I have the normal force in the plus y direction, and I have the weight in the minus y direction. So I just add up those forces as so, and I can quickly solve and find that the normal force is equal to the weight, and we have an equation for weight. It's equal to mg. Okay? So at that point, we can now plug into this formula for the normal force. The normal force is equal to mg. Okay, so our mass is going to cancel, and we end up with a formula where V max is equal to the square root of mu sub s g times r. Okay, so that's a really nice result. That is the equation for the maximum speed that we can go around a corner in our car. Right, so it depends on the radius of the circle. The bigger the radius of that circle, the larger the speed we can go around that corner without slipping, so that makes sense. And it also depends on this coefficient of static friction. Right, the larger that coefficient, the faster we can go around a corner. Right, if we have better tires that has a better coefficient of static friction with the ground, we can go around the corner faster. Right, race cars have better tires than the tires on your car. Right, they can go around these corners faster. And just to plug in a couple numbers here, so I don't have much room here, but let me do so. We can look up just two quick numbers. On dry pavement, the coefficient of static friction between rubber and pavement is mu sub s is equal to 1, and so that means, as we see here, the square root of mu sub s is equal to 1. Okay, where on wet pavement, mu sub s goes down a lot. Mu sub s is equal to 0.3 for a rubber tire on wet pavement. And so that means the square root of mu sub s is equal to about 0.5. So what this is telling us is if we have wet roads, the maximum speed that we can drive around a corner is about half as big. Right, so that is a really important point. If it's raining out, you should slow down in your car. So I hope you enjoyed this problem. I think it's really relevant to our everyday life, and it really nicely demonstrates how to solve problems both with circular motion, where we replace our acceleration with the centripetal acceleration equation, as we did right here. Right, so we at some point just made a change and used that equation that we know, and we also used our equations for both our conceptual understanding and our equations for static friction. Right, so that was important in solving this problem. Okay, let me know if you have any questions.